Hop on! I've prepared a tour around Earth's fellow planets. Let's start with Mercury, the smallest planet in the solar system. During the day, the temperature on the surface of this planet can reach 800 degrees Fahrenheit, and during the night, it can drop to negative 290 degrees Fahrenheit. The temperatures here are so extreme because the planet has no atmosphere. Instead of it, Mercury has a thin exosphere. That's one of the reasons why Mercury is not habitable. The temperatures and solar radiation are too extreme for any organism to survive there. Now let's imagine there's a way to live on Mercury. Then what would life there look like? Mercury's surface resembles that of the Moon. Over time, meteorites left lots of marks on it. Unlike the Moon's surface, Mercury is grayish-brown. Now look up. The Sun on Mercury would appear almost 3 times as large as it does on Earth. The sunlight would be almost 7 times brighter. I wonder what type of sunglasses people would wear if we lived there. Can life appear on this planet in the future? Don't get your hopes up, it's very unlikely. Now, how about landing on Venus? You might think the hottest planet in our solar system is Mercury since it's the closest to the Sun. But in reality, this title goes to Venus. What is it that makes Venus boil? The biggest reason is its atmosphere. It's made up almost entirely of carbon dioxide. The atmosphere is so thick that it leads to the planet warming up non-stop. Basically, the gases in the atmosphere prevent thermal radiation from leaving Venus. So, the planet simply can't cool down. The water on its surface constantly turns into vapor. If the surface of Venus was food, then its atmosphere would be the microwave. That's why the temperatures in this world can go up to 870 degrees Fahrenheit. What would it be like to live on Venus? On Earth, seasons change because of the planet's tilt, but Venus doesn't experience any significant changes throughout the year. Things are pretty constant at night and during the day too. And what about the view of the sky? The clouds on Venus appear yellow or bright white. They're mostly made of poisonous sulfuric acid, but then why does Venus appear reddish-orange when you look at it from Earth? Talking about the true colors of planets can be a tricky business. The hue of a space body might be different when you look at it from another planet. If we traveled all the way to Venus, a reddish-brown surface would welcome us. The molecules of carbon dioxide and sulfuric acid block sunlight coming into Venus's surface, hence the reddish-orange color of the planet. Oh, and did you know that Venus is often called Earth's twin? Both planets are nearly equal in size. Both have relatively young surfaces and thick atmospheres with clouds. Plus, the orbit of Venus is also the closest to Earth. That might raise a question about the possibility of life on Venus. I'm sorry to break the news, but nope. Venus is not habitable. The next destination is Mars. Unlike Venus, Mars has seasons due to the planet's tilt on its axis. It also has a secondary seasonal effect caused by its highly elliptical orbit. The southern hemisphere has colder winters and hotter summers than those in the northern hemisphere. The average temperature on Mars is negative 80 degrees Fahrenheit. But temperatures can also range from the poles to the equator, and they can change very dramatically within a single week. Still, not that bad compared to the previous 2 planets, huh? Is Mars habitable? The number one thing a living organism should worry about here is space radiation. Earth has a magnetic field and a thick atmosphere to protect its surface from radiation. Mars has neither. The planet's gravity is 1/3 of Earth's. So, weaker gravity and a thinner atmosphere make it harder for any living being to survive on the red planet. In 2013, NASA reported an ancient freshwater lake that could have been a hospitable environment for microbial life. This is evidence now that liquid water once flowed on Mars. This confirmation suggests that Mars could have had the necessary environment to support life. But what happened to the water on Mars? The most popular explanation is that the planet's atmosphere became too thin and cold to keep liquid water on Mars's surface. The disappearance of water might also be related to the loss of early magnetic fields. Or the reason might be the red planet's size. Mars is probably too small to keep water. So, for now, Mars is not habitable. But, you know, scientists keep sending missions to Mars. Maybe they'll find some new information. Let's wait and see. Now, Jupiter. Have you ever wondered what it might be like to live on the biggest planet in our solar system? Jupiter's environment is an unlikely place to support life. The temperatures on this planet and its composition are too extreme for any organisms to appear there. Jupiter has layers of gas, mostly hydrogen and helium. These gases fill the entire planet. Quite literally, there is no solid surface on the planet. Gases go all the way to the core, below the surface. They become liquid and turn into plasma because the atmospheric pressure there is way more intense than any place on Earth. To put it into perspective, an organism on Jupiter has to resist 1,000 times more atmospheric pressure than it would on Earth. Can a living being survive in such conditions? Unlikely. Jupiter is completely uninhabitable. But hey, have you heard that its moon Europa might be a possible habitable zone? Change of scenery. Saturn. It's the second largest planet in our solar system. Like Jupiter, Saturn is a gas giant ball mainly consisting of hydrogen and helium. What about temperatures on Saturn? It's freezing. Plus, there are extremely powerful winds there. The winds in Saturn's upper atmosphere reach the speed of 1,600 feet per second. Let's compare them to storms on Earth to have a better understanding. The strongest hurricane ever recorded on Earth was moving at 350 feet per second. So the answer to the question, is there life on Saturn? Seems pretty obvious. Life, as we understand it, doesn't exist there. The next stop is Uranus, one of the largest ice giants. Uranus's atmosphere is dominated by ice, but it's not the only reason that causes the planet's blue color. It's also the methane in the atmosphere. It absorbs red light and reflects blue. The same goes for Neptune. Uranus is the coldest planet in the solar system. The temperatures there can be as low as negative 371 degrees Fahrenheit. Life on Earth needs sunlight to get energy, but there's nothing on Uranus that can produce any energy for life forms to thrive. The bottom line is Uranus doesn't have the environment to sustain life. Heading for Neptune, the second ice giant. What is there on the planet furthest from the Sun? Obviously, it's incredibly chilly. There's neither a source of energy that bacterial life can exploit, nor a source of liquid water. Currently, scientists believe it's unlikely to find life on Neptune because of such unfriendly conditions. So, what makes our planet so livable? And I'm not just talking about human life, I mean any living organisms, even microbes. Life requires very special conditions to exist. All living beings need some sort of food, water, and the right temperature to develop. The atmosphere is a vital element. Humans, for instance, need oxygen to breathe, and they can only survive in temperatures that aren't extremely hot or cold. Another thing is gravity. All the other planets I've mentioned don't have exactly the same conditions as Earth. Life there would probably be different than what we have here. All living beings on Earth have adapted to our atmosphere, and life forms elsewhere would need to be able to survive in that planet's conditions.
Electronic satellites suddenly go out of control. There are voltage surges across the globe. In some places, there's a complete blackout. Scientists have little data on this incredible solar behavior, so we're still unable to accurately predict how or when exactly the next geomagnetic storm will happen. One such event took place back in July 2012, but thankfully it missed us. Not by far, though, by a mere 9 days. Just to give you a glimpse of what nearly happened, I need to explain some astronomical basics. A solar storm is a series of effects we feel here on Earth after certain events occur on the Sun. Our star is nothing more than a huge ball of molten gases that are constantly moving around, so these events happen more often than you'd think. For a solar storm to begin, our Sun needs to emit bursts of energy. They're in the form of solar flares and coronal mass ejections. These two phenomena send electrical charges and waves of magnetic fields toward the Earth at an astonishing speed of about 3 million miles per hour. When these solar storms reach our planet, we can see northern lights display in locations close to the Arctic Circle. But they can also mess up satellites or other types of electronic communications. Some of these solar storms can be dangerous, and back in 2012, we came close to experiencing a very powerful one that could have had a serious outcome. the most powerful in as much as 150-plus years based on research done by astronomers. But how did we manage to escape it? Did we have something to do with it, or was it just a pure coincidence? What we do know is that one of those coronal mass ejections did hit the Earth's orbit in late July 2012. Our planet had already left that specific location as it was on its scheduled trajectory around the Sun. So you might be asking yourself at this point, what if it didn't miss us? Turns out these intense solar storms are dangerous to all sorts of technological objects. Given we are now literally surrounded by electric objects, from our phones to our cars, try to imagine what would happen if they all stopped working all of a sudden. And here's how they work. Solar storms start with an explosion, or a solar flare. Then X-rays and UV radiation travel to our Earth at the speed of light. Some of the side effects? Well, they can include radio blackouts and GPS navigation errors. The effects can continue as minutes, or at times hours later, energetic particles reach our atmosphere. They move only a bit slower than the speed of light, but they can electrically shock the Earth's satellites and damage their components. Lastly, about a day later, clouds of magnetized plasma reach us as well. They can cause huge power blackouts, more or less paralyzing everything with an electrical plug. We might not even be able to flush our toilets, since most water supplies in cities use electric pumps these days. The effects of these geomagnetic storms would be different around the world, though. Solar storms are curious by themselves, but why do they affect some locations on Earth more than others? Based on recent research, geology has a lot to do with it. But I need to take you back a bit to paint you the bigger picture. Buckle up, because we're taking a trip in the time machine to a time when the moon didn't even exist yet. 4.6 billion years ago, our solar system looked a lot different than it does now, and that's putting it lightly. Hundreds of new planets began to form around the new sun. Planets like our own Earth, Venus, or Mars were still hurtling around the cosmos. Back in the 1970s, an astronomer named Donald R. Davis developed a theory that said the moon was born when another planet hit a newly formed Earth about 4.5 billion years ago. He also indicated that it might have been the size of Mars and later named this planet Theia. It's difficult to imagine what that impact might have looked like, even with the equipment we have these days. The astronomers suggested the giant impact hypothesis, trying to piece together this mystery. After running into our planet, the outer rocky layers of both Earth and Theia were projected into a circle of cosmic matter. Out of this debris, what we now know as the Moon was born. The Earth's core has apparently consumed Theia's iron core, that is, if it had any. Our planet also got into the position it occupies today. This way, it became more susceptible to geomagnetic storms. Back then, there was little to no information as to what might have happened to Theia, apart from giving us our only natural satellite. It took several years for a series of scientists to come up with an exciting new idea that revolutionized what we knew about our planet. What was left out of Theia is hiding under two continent-sized layers of rock deep within our planet. This theory is also one of the only explanations for why the moon is so dry and doesn't have much of an iron core. But why is geology so important when it comes to geomagnetic storms? Well, that's because recent data revealed that the type of rocks below your feet can affect how well your city adapts after powerful geomagnetic storms. Some types of rock, like sedimentary rocks, for example, generally have more space filled with water, which makes them electrically conductive. Other types of rocks are denser and have more resistance when it comes to electricity. Whenever such a storm happens, people living in the New England Highlands may have a higher risk of experiencing major disruptions. At the same time, those in the mid-Atlantic coastal plain have less to worry about, simply due to what's hidden beneath their cities. How did we know how scary these storms are? Well, this wasn't the first time it happened. Solar storms have dazzled the astronomer community for many years now. The most iconic event of this magnitude was the Carrington event, which happened way back in September 1859. It gave us a sneak peek of what the power of the sun is, to say the least. They named it after an English astronomer, Richard Carrington, who witnessed the solar flares himself. The power of that solar storm was something humans had never experienced before. The strong geomagnetic storm caused northern lights as far down south as the territory of Hawaii. On the morning of September 1, 1859, Richard Carrington made his way into his private observatory, located outside of London. He opened the observatory dome to have a complete view of the sky and directed his telescope to the location of the sun. He saw a bunch of huge dark spots that gleamed on the surface of our star. Shortly enough, Carrington noticed two enigmatic areas, intensely bright and full of white light bursting out from the sunspots. They disappeared 5 minutes later, but the effects carried on all across the Earth's surface. At first, later in the night, telegraph communications all around the world started to malfunction. Flashes of light started to burst from telegraph machines, disturbing the operators and even setting papers on fire. Brightly colored auroras started to appear in the nighttime skies all over the world, making confused birds chirp at night. Some people even began their daily activities, since they mistakenly thought the day had already begun. These days, our planet is laced with a mega information web, so the impact of such a solar storm would be even messier. Back in the 1800s, the telegraph system was just starting out, but this Victorian internet was an important way of sending news and private messages. Even in the United States, telegraph operators had noticed local interruptions because of thunderstorms and northern lights before. But the Carrington event and its effects were something they had never seen before. A lot of telegraph lines in North America became useless. One telegraph manager based in Pittsburgh even recalled that the currents flowing through the wires were so strong their platinum contacts were in danger of melting. Another example was that of a telegraph operator located in Washington, D.C., named Frederick W. Royce, who was hurt as his forehead touched a ground wire. Samples taken from the Earth's icy locations tell us that the Carrington effect was twice as big as any other solar storm experienced in the last 500 years. It's very difficult to imagine what the impact of a storm of that magnitude might be today. But based on a 2008 report drafted by the National Academy of Sciences, it might cost us between $1 trillion and $2 trillion in damages. There are things we can do individually to help reduce the amount of damage, though, like buying a generator or installing a backup energy supply. This can be either a solar panel or a wind turbine. More so, we can equip our houses with surge protectors that connect to our electrical panels and can save us from lightning and other power surges. The simplest solution of them all? Just unplug all the devices you're not using at any particular moment. If they aren't connected to a power source, they can't be affected by any surges.
Is it possible to put out the sun? For example, what would happen if we poured all of the Earth's oceans on it, or even more water? Well, let's find out. The universe is a place full of mysteries. Since ancient times, scientists have been arguing about how space works, but none of us has ever doubted the existence of one thing: the sun. The center of our solar system. It's big, bright, and immortal? Nah, not really. Actually, the sun is just an ordinary star. It consists of 75% hydrogen, a little helium, and a pinch of other heavy elements. Gravity holds it all together. But in around 5 billion years, the life cycle of the sun will come to an end. The hydrogen inside it will run out. Our star will begin to grow gradually, and you can't even imagine just how big it will become. And then it will start eating all the nearby planets. That's when we'll regret being so close to it. After eating us all, the star will remain a red giant for another billion years or so. And then, sooner or later, it will begin to shrink and fade, turning into a white dwarf. In the end, nothing will remain of it but a bright and colorful planetary nebula. But don't get scared. Right now, the Sun is in the middle of its life cycle. It was born about 4.5 billion years ago, and about the same amount of time remains. Fortunately, we were born during the star's best and most stable period. In other words, there's no reason to worry. So let's find one. How about speeding up the Sun's life cycle with the help of water? We'll try to collect all the water on Earth and pour it onto the Sun. First, we'll need a bucket. No, not this one. We'll need a really, really big bucket. The one that can contain around 326 million cubic miles of water. It will be equal in size to the distance from Washington to Chicago. Or if we can only find ordinary buckets, there should be around 70 quintillion of them. This is a number with 18 zeros. Okay, imagine that we magically got that many buckets. It's time to put out the Sun. We splash the star with all this water and nothing? Seriously? Oh, just look at this. The Sun has probably felt sorry for us and produced one little solar flare. It turns out that all water on Earth is actually just a pathetic drop for the Sun. People often underestimate how much bigger the Sun really is than our planet. In reality, it can fit more than 1,003,000 Earths. So yes, the Sun won't go out or even get colder. It won't even notice that we've done something. But let's not give up. We really want the Sun to go out for some reason. What happens if we pour just enough water on it? And how much is this enough? Remember our quintillions of buckets? Well, we actually need about 370 octillions of them. This number has 27 zeros. It's hard to even imagine, so let's just say that it's a lot of water. Now, let's splash it all over the Sun again. Wow, just look at the steam! But the Sun hasn't gone out again. On the contrary, it said thank you and suddenly became much bigger and brighter. What's happening? You see, the Sun isn't actually a campfire. Inside bonfires, candle flames, there's a chemical combustion. When we pour water on the fire, the water absorbs the heat of the flame and cools it to such an extent that it can no longer maintain the burning reaction. It also blocks the fire's access to oxygen. Water basically stops the chemical process. But the burning of the Sun isn't the same reaction. Even though we say it burns, it's not entirely true. What happens there is called nuclear fusion. It's one of the most violent and craziest reactions in the universe. There are many layers of hydrogen going deep into the Sun. If you take 4 hydrogen atoms and ram them together, you're left with an atom of helium. When we talk about the Sun, the process is a little more complicated. When the star tries to carry out that fusion, positive protons repel each other. It takes a lot of force and energy to somehow squeeze them together. Fortunately, there's a magical force in space. It's gravity. The Sun takes up 99.8% of all the mass of the solar system. Pretty heavy, right? And all this mass is what holds the Sun together with the help of an incredible gravitational force. So, gravity takes quadrillions of these little hydrogen atoms and pushes them together every second of every day. And when they collide, they release some energy. So, unlike fire, the Sun doesn't need oxygen to live. It needs hydrogen. And we all know that water is H2O. It consists of hydrogen and oxygen. So this is literally fuel for the Sun. It's like trying to put out a fire with gasoline. More importantly, the extra mass added by water will make the Sun heavier. Now, gravity says, thank you for your help. And then it starts to collide protons with each other even faster. And thanks to this, the synthesis speeds up. Great, we've made the Sun incredibly strong, and now it has eaten us, along with other nearby planets. And if we keep adding water, the Sun will sooner or later collapse in on itself. It will blow off its outer layers and become a black hole. Awesome! Now it will pull inside absolutely everything around. Good job, guys. Let's press rewind because clearly our water experiment was a mistake. One small solar flare sounds much better. Alright, we're back to our usual calm Sun. But it seems like there's something that we've forgotten. Well, apparently, water was critically important for life on Earth. Who would have thought? Now there's a huge amount of unmoving fish and other marine creatures lying around where the oceans used to be. Poor things. As for deep-sea creatures, they simply didn't withstand such a sharp change in pressure. Algae and corals have also dried up. Wait a minute, weren't they responsible for producing 50 to 80% of the world's oxygen? Oops, it's time to put on some oxygen masks. And how are things on dry land? I mean, now everything is just land. But you get the point. Wow, this whole place is lit, and I mean it literally. If there are no oceans, then there are no clouds or rain. Now there are forest fires everywhere. Poor animals have to escape and leave their homes. Oh my. And it's not like they'll be able to find a new home, because all plants, of course, will dry up quickly. There will be literally no place for living left on the planet. So now Earth looks like a giant desert. Great! But people have been living in deserts for thousands of years, right? Maybe they'll know what to do. They won't. After all, people in the desert also need to drink. So now there's total chaos everywhere, and survivors fight for the last drops of water. If there are any survivors at all. In fact, no matter how much they fight for resources, their fate is sealed. The ocean absorbs a huge amount of CO2 and the heat coming from the sun. They also distribute this heat throughout the planet, making it pleasant to live on. But once they're gone, the temperatures will quickly jump to 250 degrees Fahrenheit and above. But even if we forget about the high temperatures, now we have no clouds, and they helped us too, by not letting through solar radiation. So we're also under the direct impact of the sun's rays. Our last hope is icebergs. Now that everything is terribly hot, they've melted. And maybe they'll be the last hope for humanity. But that cool solar flare was definitely worth it. Silly humans.
That's it for today. So hey, if you pacified your curiosity, then give the video a like and share it with your friends. Or if you want more, just click on these videos and stay on the bright side.